So excited to be here. This conference has been so awesome so far, and this is my first time at Wasm IO, so I'm super excited. Let's just jump right into it. So today we're going to be talking about unlocking observability with WebAssembly. Observability and WebAssembly with OpenTelemetry. My name's Caleb Schoepp. I'm a software engineer at Fermyon. I've been there for about 2 years, and I'm also a spin maintainer, primarily on the SpinCube stuff that we're doing. I'm from Edmonton, Alberta in Canada. I took a picture when I left. There was snow on the ground. I was hoping there would be no snow when I get back, but I just heard that 15 centimeters of snow came down today. So no such luck, I think. And I'm online at calebschoepp.com. So just before we hop in today, I want to give a kind of table of contents what we're going to be covering today. We're going to start with building a baseline we can work from of understanding why observability is important, and also understanding what OpenTelemetry is and what that's doing. We'll talk about the 3 places you can collect telemetry data in WebAssembly. Then we're going to talk a little bit about WebAssembly runtime auto-instrumentation and the future of what that could look like for the community. We'll spend some time exploring emitting traces from your WebAssembly components using WASI OTel. And then we're going to talk a little bit about the design and progress of the WASI OTel proposal. OK, so most of us in this room probably know this already, but I want to make sure we have a baseline here. What is observability? Observability is fundamentally being able to ask questions about your system, arbitrary questions from the outside, and understand what's going on. As we have these more and more complex microservice architectures, it's hard to debug them and understand what's going on, and observability gives us the tools to answer these questions. Throughout the presentation, you're going to hear me shortening observability to OLI, or O11Y. That's just, if you don't know, because there's 11 characters between the O and the Y. OK, why does observability matter to WebAssembly, though? I think there's a couple answers to this question. One of them is just that WebAssembly is getting really popular, and with it getting super popular, it's being put into production in all sorts of different use cases. And obviously, with putting things into production, we need to be able to observe that and debug those systems. The second reason that I feel like it's important to have observability in WebAssembly is because we get some really cool features out of the runtime. We'll be talking in a second about auto-instrumentation, and there's really cool things we can do there with the WebAssembly runtimes. So now understanding what observability is, what's OpenTelemetry? OpenTelemetry is simply just an open source framework for observability. You're going to hear me shortening this to OTel throughout the presentation if you haven't heard that before. And some of the main things it's doing is it's standardizing the observability community and preventing vendor lock-in. And in fact, it's actually the second most popular and committed to CNCF project just behind Kubernetes, which is quite a feat. So there's kind of 2 big things that OpenTelemetry is helping us do. The first one is it's helping you to instrument your code to produce telemetry data. Another term they use for this is signals, and there's 3 different types of signals or telemetry you can produce. The first is just bog standard logs that we're all used to. We've all done this, we've all seen this. The main thing to note here is typically in OpenTelemetry, you'll be using whatever's standard in your programming language, and then you'll use a bridging layer to send that logs over to the OpenTelemetry system. Second thing we're all probably familiar with is metrics, just measuring values over time. There's counters, gauges, histograms, things like that. And this is answering questions like, what's the request count my app is receiving, or CPU usage over time. The third is traces. And so a trace just consists of a bunch of different spans, where each span has a start time and an end time, and a name and a bunch of metadata associated with it. And that span's measuring a unit of work, so perhaps a call from a client, or an API responding to that call. Where they get useful, though, is we combine all these spans together in a trace by linking them in parent-child relationships. And by doing this, we can understand the relationship of how things are flowing through our code, and we can understand timing relationships of how long things take. So that's all pretty handy, but it gets even handier when you talk about distributed tracing, which is just, what if I could understand the flow of requests through my entire microservice architecture? So on the left here, we have a graph of a couple of services in our architecture. We've got service A, which is calling services B and E, and then B is calling services C and D. And we can see on the right the spans that all these services are producing are tied into a distributed trace. So you'll note that under A, it's calling B, and then later it's calling E, and under B, it's got the spans for C and D. Now, importantly, when we're sending requests through a system like this, we need a way to distribute the context of this trace through the system, right? Because each span is emitted from different service, so we need a way to tie them together. And so typically, if, for example, you have HTTP requests going between services, you would like stick a trace context header in the HTTP request, and then it would be able to tie that all together. OK, so going forward, we're going to be focusing on tracing. And just quickly, the second thing OTel helps us with is to collect, process, and forward your telemetry data. So we've got the OTel collector, which helps us do that. It allows you to take in telemetry data from your source code, your programs you're running, your infrastructure, maybe like Kubernetes, data systems like Postgres, or even other collectors that are forwarding data, put it into the OTel collector, and then forward it off to a bunch of different backends. Proprietary backends like Datadog or Honeycomb, and open source backends like Jaeger or Prometheus. This is the main thing that allows us to prevent vendor lock-in. OK, so let's bring it back to WebAssembly and see what these two can do together. I want to kind of present a simple model of a component executing on a host. Imagine you have a WebAssembly host, and you have a component that you're running on that, and maybe that's providing a WASI incoming handler, and that's receiving HTTP requests. It's also maybe using some key value operations provided by the host. And then let's also just say that this component's communicating with another WebAssembly component over some arbitrary do something interface that you've defined. There's 3 places in this kind of sample setup where you could imagine collecting telemetry. The first is in what I like to call the host-guest kind of interaction. So you can emit host-guest telemetry. The second is inter-guest telemetry, that is emitting telemetry about all the communications between different guest components. And then the third is, what if we could actually emit tracing from within one of the components itself, or what I'm calling intra-guest telemetry. So going back to host-guest telemetry, and what I alluded to earlier, one of the really nice things about WebAssembly runtimes is that it gives us host-guest telemetry just out of the box, auto-instrumented, without you having to do anything to instrument it. I'm going to be demoing this in Spin, which we've all probably heard a lot about this weekend, but just briefly if you haven't heard, it's an open source tool for serverless WebAssembly that was recently accepted into the CNCF, which is super exciting. And it's really just helping you in the full life cycle of an application, templating out a new one, compiling that to WebAssembly with spin build, and then running it with spin up. OK, so let's go over to a demo here. And I'm going to pull up my terminal here. And I'm in auto instrumentation, and I will pull up the code here. So what we've got here is just a simple spin application. It's written in Rust. You can see it's just a simple function here. We're using this macro here to declare that it should be handling HTTP requests. And then we're just doing some really simple things in it. We're printing out Wasm hearts OTel. And then we're opening a key value store and just setting an arbitrary value in it. And then we're just returning a simple response there. Now, the developer flow, I don't want to spend too much time on it, but you would just go ahead and spin build the app. I've already got it built there to avoid any demo woes. And then now, normally what you would do is you would run spin up to execute the app and run that locally to test it. But since we want to do auto instrumentation, we need to wire up the host to the OpenTelemetry collector that we have running locally. And we need to start running an OpenTelemetry collector locally. So thankfully, there's a plugin in Spin that makes this super easy. There's the Spin OTel plugin. And this allows you to easily set up OpenTelemetry resources like the collector locally to do these kinds of things with the setup command. So I've already done that. And if I were just to go docker ps, we can see I've got collector running, Jaeger running, and a couple things like that. So now I can just go ahead and do spin OTel up, which is the same as spin up, but it's just sourcing the environment variable so it can talk to the OpenTelemetry collector. OK, so we'll run the application here. And then we'll go ahead and curl the application. We can see we got the print statement printed out, and we got the response back from the app. And now if I were to go spin OTel open Jaeger, this will go ahead and open in my browser Jaeger, and we can find traces, and we see that we have one here. And this is the auto instrumentation that it's producing. So if we look, there's 4 spans being created. The first top-level span, that root span there, is for the GET request. So a GET request was made against that /path. And then we can see that the host was executing a component, the component auto instrumentation. And then we can see during the execution of that component was consuming some host resources. So it was interacting with the key value, it was opening that key value, and it was setting some values in that key value. Perfect. So obviously, this is like a pretty stripped down, simple example that is maybe not too exciting, but I think it demonstrates the potential of what this auto instrumentation can do. As you start to have more complex applications, it'll be handy to have this kind of auto instrumentation. And just to show here, if I were to go ahead and send a post request to this, we would come back here, and we would see that this is, of course, showing posts now. So the beginnings of giving Sue some rough telemetry to understand your application. OK, so let's go back here and dive in. Perfect. OK, so we can't only talk about host-guest telemetry without talking about inter-guest telemetry, because in my mind, that's the much more exciting part about this auto instrumentation work. So again, inter-guest telemetry is tracing this interaction between guest modules. And the way that this works is dependent on the runtime and dependent on how you do component composition. So if you're doing dynamic composition, maybe your runtime allows you to communicate to another guest running on a WebAssembly runtime across the network somewhere. Or maybe it allows you to communicate in different runtimes on the same machine, but different hosts. If you're doing that kind of dynamic composition, fundamentally, you're just making a host call between these two components. And so in this case, inter-guest telemetry is actually kind of trivial, because we're just doing more things in the host. And so we can just trivially emit some telemetry at that point. Where it gets a little trickier and more interesting is in statically composed components. So for example, in Spin, we support statically composed components. And when you hand that off to the runtime, it just sees this single component. And there's not as clear of a path for the host to emit something at that boundary between those two components. Thankfully, there is things we can do. For example, we could work in the future to add support in Wasm time, because it is aware about that boundary, to add some instrumentation hooks into that point. But no such work has been done to do that yet. So a lot of room for improvement there. The other option we have to explore is we could do composition where we add an adapter module. So imagine we have this do something interface. We could put an adapter component in between that virtualizes that interface, just transparently passing through to the backing component. But by virtualizing it, it also would emit some telemetry data that could trace that interaction. So let's run back auto instrumentation, kind of figure out the pros and cons here. The big obvious one is that there's no effort required from the developer. You just very conveniently get this telemetry out of the box, which is handy. It's cross-language, obviously, because we basically get that out of WebAssembly. With WebAssembly being polyglot, you don't need to worry about that. You just hand it your components, and you'll get your tracing. And also, there's a really bright future, I think, with what we can do with the inter-guest telemetry stuff. So lots of room to grow there. The main obvious problem with this auto instrumentation is it's not customizable. You can't emit spans according to your own business logic or things that matter to you. You're just kind of stuck with what you get from auto instrumentation. So that obviously leads us to the third place we can emit telemetry, which is intra-guest telemetry. So let's dive into that. And before we do that, we need to understand a little bit more about tracing instrumentation, specifically how you do instrumentation with OpenTelemetry. So let's do that. Imagine you have a program, just some Rust or Go program, and you want to trace it. You're using the OpenTelemetry SDKs, so you're going to start with a tracer provider. And that tracer provider is going to allow you to create a tracer. Now, you can, of course, create multiple tracers. It allows that, and you'll typically do that if you want to have like a different tracer for different scopes of the code base. But in practice, most of the time, you'll just have a single tracer that you're using. With the tracer, whenever you want to start tracing an individual unit of work, a span, you'll create a span. And typically, you'll want to take some sort of external trace context and use that to parent the span. So imagine you've got like your incoming handler, and it's handling a request coming in. That request might have some context from your distributed services that you want to reparent that span under. So we've got this external trace context. And to tie that into this span, we're going to use something called a propagator. And that propagator can support a variety of different formats, but typically it looks like a text map propagator, which is basically pulling the standard trace context format out of your HTTP request headers and then parsing that out. So with that context in hand, we're going to hand that off to the span, create it with the proper parent-child relationships. And then when the span's first created, that's going to trigger onStart for your span processors. Now, in an OpenTelemetry instrumentation stack like this, you could have one processor, you could have multiple processors, and the processors are doing things like batching your spans, that's kind of the typical use case, or they might be doing things like mutating the spans slightly for certain use cases or printing them out, things like that. In practice, most of the time, you basically just have a batching span processor here. OnStart's called with the span, you do your thing in your code, eventually that span's going to end. You're going to call onEnd on it, which will also trigger the span processor. And then that's going to go ahead and say, OK, you're done with this span. I'm going to let the span exporter know that it's good to export this span now, because we've finished it and it has all the metadata we need to send off. So we've got our span exporter here, and then that's responsible for actually getting this metadata out of the process to the OpenTelemetry collector that you have running maybe as a sidecar or a daemon near your program. So that's the flow of tracing instrumentation with OpenTelemetry. Which, side note, if any of that got you excited, I would highly recommend the OTel specification. I've been turning into a bit of a specification nerd, and I actually quite enjoyed that. So link there if you're interested. Great. So let's come back to the intra-guest telemetry. We really kind of have two options for how we can do this based on the instrumentation if we want to tie into this OpenTelemetry SDKs. The first option is we can use just a standard HTTP exporter backed by WASI HTTP. So let's go back to that diagram. We've got this same program, but this time it's running as a component inside a WebAssembly host. That's what that new purple box is. And we were using all the same OpenTelemetry SDK tooling. Nothing's changed about our program. But this time, we're using an exporter that's backed by WASI HTTP. And I failed to mention earlier that typically the exporter is either using HTTP or gRPC protocols, more commonly HTTP though. And so with this exporter, as long as we've got outbound WASI HTTP supported, we can just directly export these spans outside of the component and send them off to the collector, just directly, kind of normally like you would expect to. Some folks from the Wasm Cloud community, Jonas and Lucas, did some really great work around this, exploring what that would look like with Go components. And they did some work to create some libraries that enables this use case, if you want to explore that. There's pros and cons to this approach. The pro is that it's really familiar. You're basically just taking exactly your normal non-WebAssembly program and compiling it to WebAssembly, and it sort of just works. The downsides is that it's not quite as easy to compile the OpenTelemetry libraries to WebAssembly as you would hope. They had to do quite a bit of finagling to get that to work. And then on top of that, there's kind of two other disadvantages. The first one is that you can't get the parent trace context in non-HTTP components. So what does that mean? That's kind of a mouthful. This is what we would want the trace to look like. We have a span for the GET request that comes into the host. We have a span for the host executing that component. And then we have the guest itself emitting this span that's tied into this trace, properly parented into this trace. And you can do this for HTTP components because you have the host literally mutate the HTTP request that it's handing off to that component and stick into the header the appropriate trace context. So the host goes, oh, I know I'm currently in this execute WASM component span, stick that in the header, and then the guest can get access to that information. But you're kind of just screwed if you're using non-HTTP components where there's not standards for how to pass this trace context. For example, if you're listening on like a Redis channel, you have your my channel receive span, then your execute WASM component foo span, and then the guest's going to emit this, but it has no way to get this parent trace context and tie into that. The second disadvantage with the approach of using an HTTP exporter is that you can't associate host operations with the trace. So again, what does that mean? This is what we would want as like an ideal trace. Get request, execute the component, the guest emits a span, and then during the work the guest is doing, it's using that key value as an example. It's opening the store, and it's maybe setting a value in that store. You want those host operations to be tied in as children of that guest span. They should be properly parented like that. But you're not able to do that, unfortunately. You can't tie those in. Those would show up as a different span. And the reason is because when the guest is emitting that span, the host has no knowledge of it. So they're both emitting spans at the same time without knowledge of each other, and so the host can't properly parent those KV spans under the guest span. So this kind of naturally leads us to finding another approach, and that's option number 2, which is a special WASI processor backed by WASI OTel. So what would this look like? Again, use all the same OpenTelemetry tracing SDK infrastructure here, but this time let's do away with an exporter, and we're just going to have a processor. So this time the processor is going to be backed by WASI OTel. Because the processor is backed by WASI OTel and its processor interface, we have the same on-start, on-end interfaces. But this time, because we have the on-start, the host now knows about any spans that are created by the guest, and so it's able to properly parent those child host operations under the guest span. In addition to that, we'll provide a WASI propagator, again backed by WASI OTel, which will solve the other problem we saw of parenting that guest span under the kind of root host span, because it will be able to tell the guest what the current context of the host is. Of course, you can continue to use the same old propagator from before if you want to. This is all enabled by a new WASI proposal called WASI OTel. It's currently phase 0. It's really new. We just submitted the issue to the WASI subgroup and are hoping to move that through the WASI phasal process. Let's take a look at the WIT really quick. So here's a really simplified version of the interface. We've got 3 methods. OnStart and OnEnd obviously enable the processor. OnStart basically just takes span context, which is just the unique representation of a span, its parent, its trace ID, and its like span ID. And that's what allows the host to track what spans the guest is currently creating. And then it also takes onEnd, which is, sorry, it has an onEnd function, which takes span data, which is all of the metadata of the span that it actually needs to ship off when it's done. And then we have outer span context, which enables the WASI propagator. And that basically just returns the current host context and hands that to the guest, which is basically that span that was execute component so that it can properly parent it. Wrapping around WASI OTel, because that's not a very intuitive interface to use, is a set of libraries in OpenTelemetry WASI, which basically just takes WASI OTel and wraps it up into OpenTelemetry SDKs for all the different languages. Currently, we only have support for Rust and for like the latest version, but the goal is to support all the different languages and backport to all the different OpenTelemetry versions so that people can just transparently use this. OK, so let's jump into a demo here, and we'll show what this looks like. I will kill this process, and we'll come into WASI OTel, open this guy up in code, make it a bunch bigger. Perfect. OK, so again, we just have a simple spin component here, triggered by HTTP as before. But you'll notice this time we're doing a bunch of OpenTelemetry stuff at the start. So we're starting by creating a WASI processor, which we saw in that diagram. Then we're using just standard OpenTelemetry things to create a tracer provider and a tracer. Here we're creating a WASI propagator, which is saying, OK, when you execute this component in spin, grab the context from the host and set that as the parent context of the first span you create, which means down here, and when we call tracer and span, that's properly going to be parented under the host. Here we're creating a hello Wasm IO. I'll put a couple exclamation marks there. And we can see we're setting an attribute on the span, we're adding some events to the span, and we're also doing a child span. And then we're just doing some of the same things we did before. We're printing and doing some host operations that should be properly childrened under that. OK, so if I go ahead and spin build this, and then go spin OTel up, I can go ahead and send a curl request to this, and we'll see it prints. And we get the return value. And then if we come over here to Jaeger, we should expect to see something with 6 spans. Perfect. There you go. So you can see we've got the host span, the get request, the execute component, and then now we're emitting spans directly from within content here, that helm wasm IO and the child span. And then we have proper nesting of the key value operations under that child span. Cool. OK, so let's finish by talking a little bit about WASI OTel. So for anybody who's followed this work online a little bit, you might have heard of WASI Observe, which is where this work originated as an effort by the community to explore what observability could look like for WebAssembly. And so a couple things led us down the path of moving from WASI Observe to WASI OTel. The first one was just discovering that the community has really coalesced around OpenTelemetry, and that's what customers are using and what people want to use in their applications. So we really wanted to use that directly and support that directly. And as part of supporting that directly, we wanted an interface where we could closely mirror how things work in OpenTelemetry and really tie them nicely together and move at the speed OpenTelemetry is moving at, and didn't want to burden ourselves with trying to come up with kind of a more generic interface that could maybe be directly consumed. So that's kind of the reasons we pursued WASI OTel separately. But given all that, we still think that there's space for WASI Observe to be a more generic observability interface if people want to directly consume it in components or a more clear kind of generic abstraction arises. We're just trying to land something first, basically, and learn from that. And then if something arises later, we can go with that in WASI Observe. What are next steps for WASI OTel? Whole bunch of things we got to do. It's phase 0. It literally just got submitted to the WASI phase process, so we'd love to kind of start driving that through that. We'd love to get more support and involvement from the OpenTelemetry community to really kind of dig in and see what they think about the interfaces and this user experience. WASI OTel support only exists in Spin right now on an experimental branch, so we'd love to get that further along and also see support in other runtimes. And then we'd also like to see OpenTelemetry WASI SDKs implemented in other languages like TypeScript, Go, all the different languages, and backport them to as many OpenTelemetry versions as possible. And of course, we talked about metrics and logs at the start, but focused on tracing. And that's because we haven't done any work around metrics and logs in WASI OTel. So it'd be really interesting to explore what that could look like. And finally, we're always looking for people to play around with this, get hands-on, and share their experiences with us. I couldn't have done any of this work by myself, so I want to give a big shout out to everybody who's involved in this, and particularly give a shout out to Shaker, Victor, and Lan for their huge contributions and lots of time talking with me about this. And yeah, I'd love for folks to get involved. There's a QR code up there for chatting on Zulip about this, the WASI Observe Zulip, and then there's also a link up there to go check out OpenTelemetry WASI, which is the best README right now to check out this code and play around with it. I know there's not much left of the conference, but please hunt me down and grab me if you want to chat about this. I'd love to talk. And that's all I've got today. Thank you, everyone. I think we have like 2 minutes for questions, if folks have any. Easy peasy lemon squeezy. Thank you, everybody.